Good afternoon. In biology, there is a saying of what comes first, the chicken or the egg. In engineering, there is another saying stipulating that form follows function. Today, we are going to explore drainage and drainage structures. Now, to get our mindset in the right track, let's explore the concepts of form follows function in the simplest example. The first task of function is to make a bridge between these two columns so an ant can go from column A to column B. So we place the plastic, which weighs actually a quarter of a gram, across the columns, and now an ant can cross across. Easy. Here's a piece of plastic weighing less than a quarter of a gram. The job is done. But let's see what happens if the function changes for the bridge to support a mass, let's say of 58 grams, 200 times greater than the bridge weight itself. What happens? The function fails. We'll tape the ends of the bridge so it's secured to the column. So now we have a bridge, same material. What happens when I add the weight? Oh, it works. So the process works, but does it really? So when I let go of the columns, we have introduced unforeseen, invisible forces that came into play and pulled the columns down. So the question is the task even possible with the materials we have? Well, it is, because if we take the same piece of plastic and roll it into a circle, place it across the columns, and then put the weight on top, the structure holds. So here's a simple example of form, which is the straw, follows function, the weight of the piece, and the task is completed. Now in drainage is not a simple function. To give you an example, if I open up a bottle of water, there's a hole at the end, and if we start pouring the water into a glass, we have drainage simply by gravity. However, if we pour the water and then turn it upside down, drainage stops. As you can see, the water is holding. The only thing I've changed is I poured it over the water. Now, a basic question is, in this 1 gallon jug, which drain is going to drain the jug the fastest? Is it a 1/4 inch hole, the 2 inch hole, the 1 inch hole, or the 4 inch hole? Well, obviously it's the 4 inch hole. It's the largest hole. We even developed a Hagen-Poiseuille equation that's going to explain and give you exact numbers how fast it's going to drain out of the jug. But the question is, and it's never asked or calculated, how did the water get into the jug before we drained it? If the incoming hole is only 1/4 inch, the size of the outlet holes is academic. A 1/4 hole will do it, a 4 inch hole will do it, a 2 inch hole will do it. It really doesn't matter. Another popular saying is that we have to study and understand history so that we do not repeat the problems of the past. In drainage, there was a long obsession with a 4 inch diameter hole. Actually, in 1859, Henry French used this to create what we call now the French drain. It's not the France, but it's the name of the person. So these 18-inch tiles were laid side by side with an 1/8 inch to 1/4 inch gap in between. And 100 years later, they were still in use. In fact, I still used them in 1965 in leach line applications. But the problem was they chipped, they couldn't withhold soil pressure, they were heavy and expensive to put down. So 100 years later, the clay tiles were starting to be replaced by other inventions. Orangeburg tiles, styrene tiles. They're still 4 inches, but now 10 feet long, much lighter, easier to install. We had cement asbestos pipe, now also lighter, but were still brittle. It did not survive well under soil pressure. These pipes did not solve the original problem of soil incursion as we've seen in the pictures into the pipe. And these fragile pipes were then followed by a layered 4-inch again HDPE pipe, which had structural stability, was light, came in long lengths, and instead of gaps, had 1/2-inch holes on both sides of the side. So we had a rock envelope surrounding these pipes. So in this particular pipe, which is still even used today, and the older style pipes, the pipe was frequently surrounded with what they called number 2 stone. The reason the stone was that large is we didn't want the stone to penetrate the pipe, even though by random chance, some of the stone may actually block the pipe. But regardless, putting the 3 stones together, we do have a gap between the 3 points, which is an opening which is sizable for water to move. However, this was also large enough for soil to move. So soil still infiltrated the rock, which then went into the pipe. And as we saw in the previous picture, the pipe either came plugged with silt or clay or root intrusion. So in the 1970s, we started to abandon the 1/2-inch hole configurations and we changed to slitted pipe. We had much smaller holes in the form of slits, like in this 4-inch pipe, and there were many variations that cropped up. We had smaller diameter pipes with the slits in it, all the way to large arches with slits in it. As you can probably recognize the sizes of these pipes. When we talk about soil incursion, we're really talking about soils. Now on the planet, soils are essentially composed of 3 elements. Sand, which is the largest particle, silt, second largest, and clay, which is the 3rd particle. Having different combinations of the 3, we have a different soil type. But what's unusual with these soils is once enacted with water or they're very dry, they're really fluid in nature. So let me go back to our 4-inch perforated pipe surrounded with gravel. And when we put sand over the top, see what happens. Like a pachinko game, the sand is infiltrating the interior of the pipe. So even though the slits became smaller, it did not filter out or keep the sand from entering the pipe. And again, the sand is the largest particle in soils. Silt and clay, when totally wet, are going to move even quicker and plug the pipe, as we've seen in the previous explanations. Now, to address the problem of soil incursion, in the 1980s, geowrap pipe came into scene and became the improved design. It was a fabric that covered the existing holes of the pipe. It also was used in all the other designs. The flat edge pipe had a geofabric covering on it. We had 6-inch coils of pipe with the geofabric on it. You may have seen even recently, we had a styrofoam pipe, 4-inch pipe, with styrofoam pellets around it to replace the gravel that are also wrapped in geofabric. Some are wrapped at the pipe, some are wrapped around the styrofoam itself. So all these attempts were to solve soil incursion. Did this process work? Yes, it did. Soil no longer came into the drainage pipe. But I thought the function was to move the water, not the soil. So let's test that theory. I flattened out a pipe and you end up with 2 millimeters slits wide, about 1.5 inches long, about 1.5 inches apart. So we're going to place that inside our cup and we're going to add gravel on top, no geofabric yet. And we're going to pour water onto the gravel. So the water finds its way quickly through the gravel, hits the openings, starts filling the bottom of the cup, and then exits at a fairly good rate. This is good drainage with slitted pipe. And if you can look up close, it's a fairly good flow. That's all we need. But let's change the parameter. We're going to empty the gravel. Get rid of the water. Now, on top of the disc, we're going to place the geofabric disc to cover the slits in the pipe. We'll put the gravel back on top of the geofabric, and that's the soil pressure. And we're going to repeat the process of adding water. And as you can see, it slowed down dramatically. I have to wait not to overflow because it's just dripping into the bottom section of the cup. And we'll wait till that section rises because it's still draining in a sense, but significantly slower than when the geofabric was missing. So in our first attempt without the geofabric to flow a liter of water through my 3-inch opening, it took 1 minute and 12 seconds. With the geofabric on top, the flow rate dramatically decreased with clean water, and it actually took 13 minutes and 12 seconds for 1 liter to drain through that profile. So my effectiveness was actually 13 times slower, but it still drains and prevents soil incursion. Our research department says it works, so let's bury it and market it. Now in the laboratory, using triple rinse gravel and clear water, we can definitely say we do have drainage. But in real life, we're dealing with soils, we're dealing with gravel that is not as dirty. Anytime you see a delivery truck, you probably see a cloud of dust when the gravel is dumped. Even in this small gravel exhibition here, just by shaking it, if you look at the bottom, there are very fines in the gravel formations. It doesn't take much. So what we did is we took gravel that was advertised as washed, and we rinsed it with 1 liter of water, 3,000 grams of gravel. That's enough gravel to cover maybe 1 inch of your gravel drainage formation. And the silts that are recovered in the rinsate as water passed over the gravel was little cloudy water. This is really reality. So what happens when this water now gets infiltrated over the geofabric? So we start pouring it. We have initial drainage, but then drainage immediately starts to slow down. It starts to slow down because we have convergence. The small particles that move with the water find smaller and smaller openings till eventually the system plugs. In our tests here, 1 liter of water, of reality water, passing through this membrane took actually 5 hours and 40 minutes before it emptied, 340 times slower than the original pipe without the geofabric.
see how much slower that dripping is.
Yeah. And then it slows down. So after passing 1 liter of reality water through the membrane, we took it apart, dissected it, and on the left you have the original membrane. On the right we have all the soil impingement that causes blockage on a geofabric. Just 1 liter of water through a 3-inch opening. The thing of getting the point across drainage is not simple.
It is complex and scientific.
Now, 25 years ago, in 2000, the EPIC chamber was patented and a new form was created to address drainage functions. It had an open bottom, an arch design for structural strength, a large 2-inch connection hole centered 4 inches above the bottom, large 1-inch holes on the outside, and an oval hole on the inside, 1.5 inches in diameter, to form a gravity trap. Each of these 3 holes worked together and had a strategic function. It changed how water moved into the drainage pipe. Let's see how it works with our former model. So here we have gravel, and we have an open end is partially inserted into the gravel. So when water is poured, it has to go down through the gravel, around the wall, and then well up through the gravel before it exits our 3-inch, 3/8 inch diameter pipe. So with clear water, as we pour water, the water goes down and starts to come up, hits the 3/4 inch opening, and pours out. Incidentally, in this case, it was at the same rate as without the geofabric formation, and it's constant. The more you pour, it's dictated by the diameter of the 3/8 inch hole. The big difference is now, EPIC does not use geofabrics, so even though we pour on reality water that is dirty, the flow rate doesn't change because there's no impingement on a geofabric in order for blockage to occur. So we have a pipe that doesn't plug, and you can pour whatever water you want through the profile to effectively drain. So side by side, we have the geofabric flow and we have the EPIC flow on the right. Geofabric flow, more water. Same reality water on the right. As we have just shown, geofabrics in the use, especially of drainage pipe structure, is really obsolete because of the blockage situation. And as I drink my coffee, I sometimes wonder, there must be millions of engineers across the world still designing geofabric drainage in their plans. And I wondered if they ever thought and stopped that when they drink their coffee, did they change their coffee filter? Now, as we mentioned before, soil incursion is a problem with slitted pipe because the holes are too large. Even though we use much larger holes in EPIC, soil incursion does not happen because as we flip it around, even though it enters the large holes, it is stopped by that outer chamber, and gravity keeps that gravel down and nothing really enters the pipe, even if we use sand formations because of the gravity and density differentiation. So the structure of EPIC is essentially It could be just fine gravel all the way, or we have sand going all the way in drainage applications, depending on the function you want to accomplish. Now the thing is, we don't use geofabrics because we use a bridging gravel. If the gravel is 8 times smaller than the sand above it, sand will not infiltrate the gravel formation. So drainage then is the speed of your infiltration rate of the sand, and then it accelerates once it hits the gravel. So for filtration aspects, filtration actually occurs at the surface because this is where the smallest opening occurs. So if we have an incursion of silt or clay or other debris, it is stopped within the first 1/4 inch of your surface and it can be serviced. So no matter what aggregate you use, and again we prefer that 1/4 inch 8:1 ratio gravel or what is above, what are the differences in structure? In conventional pipe, we can have the gravel again surround it, but how does drainage work? Well, the water would have to go down to the bottom and then start to rise before it interfaces the pipe and starts impinging on the geofabric. So in the meantime, we have a dead space at the bottom that is going to be stagnant and start becoming anaerobic, which is going to introduce another unforeseen problems. As the water rises, it finds other drainage openings, and then eventually the system plugs. In the EPIC design, the open bottom is again a feature. So if the groundwater is welling up into my area and I want to control it, it has no obstruction. It simply wells up right into the chamber and exits the 2-inch hole. If drainage occurs from the side or from the top, water has to travel down through the gravel, go in through the large outside holes, and then up to find that larger inner hole, and then goes into the chamber and out the 2-inch pipe. So the process is different. We have a gravity trap in play, we have a different directional flow in play, and you have drainage from whatever direction the water is coming from. If it's upwelling from the ground, if it's coming in from the side, or if it's coming in from the top. So it's important to extend your gravel layer all the way to the surface so you have an opening, or superimpose it with a sand to form the bridging gravel effect all the way to the surface. But if over here, if we cover this with native soils, we're already asking for trouble because those soils are going to migrate and impinge on the geofabric structure and your function stops. So this is where, again, we emphasize form follows the function. We have functions addressing all the problems: soil incursion, siltation, and blockage. Over here, we have a structure that doesn't do that. Thank you for watching our brief demonstration on comparing drainage differences. And if you need more information, check us out on our website, epictws.com. Thank you.